Welcome back. In this video, we are going through some Wiley Plus examples for magnetic flux, Faraday's law, and Lenz's law. In this first example, we are asked to determine the electric motive force in volts induced in the loop during the time intervals given in a graph here. So we're going to be using this equation here. Sorry, this is not right. That one is supposed to be magnetic flux. There we go. So if we were to write this equation out, we can write this as, so we know our magnetic flux is equal to dot product of dA times our magnetic field. And since they're both constant, we know that this simplifies down to just BA. So if we plug that into our EMF, this is going to give us, so we're going to start with our area out here, and we're going to do B on top. This is over T. Sorry. I'll make this a little more clear. So our area is going to be constant, and our magnetic field changes with time. And yeah, so that is going to be what this is equal to. So we're going to start with part A. And for part A, so our area is pi r squared because we are working with a loop. And this is our difference in B over our change in time. So in this case, this is like saying our slope is equal to our difference in y over our difference of x. So this represents our slope here. So we're going to write that. So this is 0.5, which is our change in our magnetic field, and our change in time, which is 2 seconds. Right, and let's plug in for radius, 0.16 squared. So this is equal to, so 0.16 squared times pi times 0.5 divided by 2. And this gives us our first value of 0.0201 volts. And you'll notice that this answer is going to be the same as C, and it's going to be 0 at interval 2 to 4. And this is because this section here has no slope, right? So that slope would be equal to 0, thus making the rest of this equation equal to 0. And if this weren't asking for the magnitude, this would be negative for C, but since it only wants a magnitude, then that's why both A and C are the same. So try that out for yourself, see if you understand it, and see if you get the same answers. Okay, moving on. Need to zoom in for this one. So we have a figure that shows a rectangle, and it's split into 3 equal areas. So the fields are uniform within each region. And we want to find what the magnitude and direction of the induced current is in the wire. Okay, so how this will work, this is kind of similar to our last question. We're going to use 2 equations. We're going to use our EMF, and since we are talking about induced currents, we are going to use Lenz's law. And we will also be using this equation here to help us find our current, which is the magnitude of our EMF over our resistance is equal to our current induced. Okay, so let's start with our first equation. It's equal to our negative of our sum of all of our fluxes, which is equal to so our area is going to be constant. And sum just means that we're considering the B1, B2, and B3. This is equal to, said our area was constant. So that is B1 over T1 plus B2 over T2 plus B3 over T3. So we're going to assume out of page is positive. And this is reflected by the slopes of each of our functions in accordance to these. Right, so our B1 is a positive slope and is out of the page. So let me zoom in so you can see better. And our B2 also has a positive slope. It's less steep. And that's out of the page. And into the page, we have B3, which has a negative slope. Our scale is set by, so this is negative 2.5 of our BS, which is equal to, so that's 5 times 10 to the negative 6 times 2.5. And this is negative, oops, oh no. Sorry. It's equal to negative 1.25 times 10 to the negative 5 in our bottom scale. And at our top scale, we have 5 times 10 to the negative 6. Okay, so now we have everything that we need. Yeah, and our time scale, I think, is just, yeah, I'm not sure if there's anything in there. Oh yeah, our time scale is given, so that's over 2 for each one. So let's start. So this is, our area is given here. So this is 0.22 times 0.27. And this is multiplied by each of our individual slopes. So this is over 2. They're all over 2 because they all end at the same interval, at least in our case that we're going to use. So for B1, we are right at the top of our scale. So this is 5 times 10 to the negative 6. And this is half of that for our second one. So this is going to be 2.5 times 10 to the negative 6. And this is negative, since we're going downwards, 1.25 times 10 to the negative 5. All right. So when we find this value, this is equal to, so let's start just with in. So this is 5 times 10 to the negative 6. It's plus 2.5 times 10 to the negative 6. And this is minus 1.25 times 10 to the negative 5. And this multiplied by our area, 0.22 times 0.27, which is equal to negative, and another negative, because we had this negative in front, which gives us positive 2.97 times 10 to the negative 7. Sorry, I forgot to divide by 2. I'm so sorry. Okay, so this is 5 times 10 to the negative 6 divided by 2, plus 2.5 times 10 to the negative 6 divided by 2, minus 1.25 times 10 to the negative 5 divided by 2, times our area. And this should give us, sorry, this equation also needs to include over 3, since we have 3 sections. Sorry, so now, there we go, there's our answer. This gives us negative 4.95 times 10 to the negative 8, which is equal to positive 4.95 times 10 to the negative 8 induced. So now we're going to take that value, going to work with our equation in red now, and when we divide it by our resistance, which is equal to 6.5 times 10 to the negative 3, this gives us, divided by 6.5 times 10 to the negative 3, this is equal to negative 7.615, and it just wants the magnitude, so we can just get rid of that negative sign after, times 10 to the negative 6 amps. All right, and since our increasing flux was in the positive direction, and according to Lenz's law, when we use our right-hand rule, our induced current must be flowing the other way, so that means we need a counterclockwise direction for this problem. Okay, next question. We've got 2 circular regions and 3 different paths to follow. And we want to calculate what our value is for the closed integral of electric field times the dot product of the path that we follow for 1, 2, and 3. So let's start with A. We're given our radiuses of our different paths, of our different regions here. So starting for A, we want what it is for path 1. So we're going to relate this equation to our Lenz's law. So when we do that, this is equal to, so we're using our right side to find our left side value, is equal to d over dt. And I'm just going to abbreviate this, right, because we already know how to find our electric flux. So I'm just short forming it. And this is going to be, hold on. So in our first path, we are going around radius 1 here. So B1 is given by 52 times 10 to the negative 3 Teslas. And our area in this case is going to be pi r1 squared, which is 0.22 meters squared. And both are decreasing at a rate of 9.40 milliteslas per second. So actually, since that's in milliteslas, I'm going to keep this in milliteslas too, and then we can just expect to get millivolts as an answer. Okay, so in this case, we've got 9.4 times 52 times pi times 0.22 squared. And this gives us second thought, I will actually put that in there. Okay, let's try again. So this is 9.4 times 10 to the negative 3 times 52 times 10 to the negative 3 times pi times 0.22 squared. Okay, I'm not getting the right answer, so let me find what I am doing wrong. Okay, I apologize. Let's redo this. Okay, so this is equal to negative change in flux over our time. this is going to be is equal to negative d over dt. So area is going to be constant, so this is pi r1 squared. And we're going to use our rate now, so this is negative 9.4 times 10 to the negative 3. And this is equal to 0.22 squared times pi times 9.4 times 10 to the negative 3. And this is equal to negative 1.429 millivolts. Okay, same thing's going to happen for B. It's equal to times our electric field and our area, which is equal to, so our new area is now R2 squared, and we still have the same rate of change. So in this case, we have as our answer, so we've got 0.327 squared times pi times 9.4 times 10 to the negative 3, and this is negative 3.1577 times 10 to the negative 3 volts. And what do we do about part C? So since we are pointing in opposite directions, when we go around our path 3, we have both inward pointing and outward pointing ones as we go around, where our outward pointing ones are the R2. So in this case, we will need to subtract. So for our third one, we will have to take our first one and subtract our second one, which in this case is negative 1.429, and this is minus negative 3.15. And in this case, this gives us, so this is negative 1.429 then minus our answer. And this will give us 1.728 times 10 to the negative 3 volts for part C. Okay. And this is our last question here. So in this picture, we have a metal rod that is forced to move along a constant velocity. So that means the induced force is going to be developed this way from Lenz's law, along two parallel metal rails connected with a strip of metal at one end. The magnetic field is 0.275 Teslas out of the page. And if the rails are separated by a certain distance and the speed of the rod is given, what was the magnitude of the EMF that's generated? And if the rod has a resistance, what's the amperes in the rod? And at what rate is energy being transferred to thermal energy? Okay, so I'm just going to convert some things. This is going to be 49.1 centimeters is equal to this is 49.1 divided by 100. This is 0.491 meters per second. So first we'll start with part A to find our EMF. So doing so, we have negative d flux over dt. So if we find our flux first, this is equal to dA And in this case, we're changing our F and our length is equal. So this is B. And since they're perpendicular, they don't have, so the angle between them is 0. So we can just write this like that. And this is equal to our length, which is our height, times our change in x, which is equal to, so our b is given by 0.275, and this is changing by, so this is 0.236 as our L, dx over dt. Sorry, dx is just here. And if we put that into this electromotive force equation, we get dx over dt times 0.275, 0.236, and then we can just replace this by our velocity, right? Because that is our rate and change of our dx over dt. This is going to be negative 0.491, and this gives us 0.031865, and we just want the magnitude. And this is in volts for electric motive force for part A. Now let's move on to part B. So if the rod has resistance, what is the current? So now we're going to use this equation here. So this is 0.031865 volts over our resistance, which is 25.4 ohms. And this gives 1.254 times 10 to the negative 3. And finally for C, we know that power is equal to I squared R. So if we do that, we have 0.031865 squared times 25.4. And this is going to give us, which will give us 3.9977 times 10 to the negative 5 watts. Okay, and that is it for this practice. I hope you enjoyed, and I hope you found this helpful. Let me know if I need to clarify anything any further. But yeah, thanks for watching, and I will see you in the next video.